Okay, today we're going to use L'Hopital's rule. For our first example, we're going to do infinity over infinity. The way L'Hopital's rule works is if you plug in your number, in this case infinity, and you notice that you get infinity over infinity, then you can use L'Hopital's rule, which says that that limit is going to equal, we're going to write L'Hopital's rule above the equal sign, and so that limit is going to equal this limit. And what I want you to notice is that we're doing the derivative of the top separately, and we're doing the derivative of the bottom separately, so it's not a quotient rule. So this is called L'Hopital's rule. When you plug in the number and it's equal to infinity over infinity, then that limit is going to equal this limit according to L'Hopital's rule, where you just do the derivative of the top and the derivative of the bottom separately. And then you can try it again. If you plug in the infinity, you would get infinity over 1. So your final answer is infinity. However, if you got infinity over infinity again, then you could use L'Hopital's rule again, and you can actually use it as many times as necessary. In this example, we only needed to use it once. Final answer here is infinity. Okay, another common type that we see is for L'Hopital's rule is going to be 0 over 0. So if you plug in your number and you get 0 over 0, then you can use L'Hopital's rule, which says that this limit is going to equal this limit right here. You'll notice we're doing the derivative separately. And because we're using L'Hopital's rule, we want to write L'Hopital's rule above the equal sign. Now, after doing those derivatives, we get this. And you notice if we just plug in the 0, we're just going to get 1 over 1. Final answer here is 1. Some of you might remember the special rule for this limit. This is one of our trig limits that we learned a while ago. We already knew that that limit was equal to 1. Okay, here's another example of infinity over infinity. The negative in front of it's not that big of a deal. Remember, that's just a constant. Because we're doing the limit as x goes to infinity, if this limit equals a number, that means the graph is actually approaching some kind of horizontal asymptote as x goes to infinity. And most of us recognize this rational function, and we know what that horizontal asymptote is. You would have to take the biggest piece on the top and the biggest piece on the bottom. You'll notice that they both are x squared. So the horizontal asymptote is going to be y equals, and then you would take the coefficients, negative 8 over 4. In this case, we get negative 2, and that would be the answer for this limit, negative 2. But I just want to show you that you can use L'Hopital's rule to get the same answer. Right now, if we plug in the infinity, you would ignore the smaller pieces, and you would get negative infinity over infinity. So we know we can use L'Hopital's rule. This limit is going to equal the limit as x goes to infinity of 3 minus 16x over 8x. I want you to notice I did the derivative of the top separately and the derivative of the bottom separately. Now we can try it again. If we plug in the infinity, you'll notice we're going to get negative infinity over infinity again. So we can do L'Hopital's rule one more time if we want to. So this limit is going to equal this limit here. And now we're doing the limit of a constant. That's just going to equal the constant, so we just get negative 2. So for this example, we had to use L'Hopital's rule twice, but we got the answer that we expected. This limit will equal negative 2. Now there are some other types of L'Hopital's rule, but for AP Calculus AB, we're pretty much just going to get 0 over 0 or infinity over infinity. Now when we plug in negative infinity, we're going to get 0 times infinity. But remember, we're supposed to either have 0 over 0 or infinity over infinity. What we can do is we can rewrite our function. So this will just be pre-calculus, so I'm rewriting it. This is the limit as x goes to negative infinity of x over e to the negative x. So now when I plug in a negative infinity, I'm going to get negative infinity over infinity. So instead of being 0 times infinity, we rewrote the function so that when we do our limit, we end up getting infinity over infinity, of course with a negative in the front of it, but this means we can use L'Hopital's rule. So this limit here is going to equal, according to L'Hopital's rule, the limit as x goes to negative infinity of, and we're going to do the derivative of x, we get 1, and the derivative of e to the negative x is going to be negative e to the negative x. Now this is just going to be a plug-in limit. When you plug in the number, you get 1 over negative e to the infinity. So that's just going to be equal to 0. Now let's take a closer look at doing the derivative of e to the negative x. the derivative of e to the x is just going to equal e to the x. But we didn't have an x, we had a negative x. So we're going to have to do the chain rule. So we got to do the derivative of negative x. So the chain rule gives us an extra -1. And that's how we're getting this extra negative on the bottom here when we use L'Hopital's rule. Okay, for this example, when you plug in the 0, it looks like you're getting 0 times, and then you can't plug a 0 into this one. So here's an example of ln of x. The limit as x goes to 0 from the right side, it's approaching -infinity. So we have 0 times -infinity. Okay, so we're going to have to rewrite this because we need it to either be 0 over 0 or infinity over infinity in order to use L'Hopital's rule. So we can rewrite this. There's two ways of doing it. We can either multiply the top and the bottom by 1 over x, we would get this. Or we can multiply the top and the bottom by 1 over ln of x, and we would get this. Now, the bottom one might look good because we know when we do the derivative of x, we're just going to get 1. So that piece is going to be really nice. But the other piece is going to be a bit of a problem. Sometimes you just have to try both ways and see which one works better. In this case, this is the wrong decision. The reason why the top one is better, because if you do the derivative for ln of x, you're just going to get 1 over x. And you'll see in the end it cancels pretty nice. Okay, let's see what happens when you plug in the 0. Okay, we already talked about ln of x. As x goes to 0 from the right, it's approaching -infinity. So right now the top is going to give us -infinity. And for 1 over x, as x goes to 0 from the right, you can see we're approaching +infinity. So the bottom gives us +infinity. But the good news is that we are getting infinity over infinity, so we can use L'Hopital's rule. So that means that this limit is going to equal this limit here. The derivative of the top is going to give me 1 over x. The derivative of the bottom is going to give me negative x to the -2. And so that's -1 over x squared. I think you can see that we can cancel one of these. And if we multiply the top and the bottom by x, we're going to get -x. Now the reason why these two cancel, and the reason why we're allowed to multiply the top and the bottom by x, is because we're doing the limit as x goes to 0, so x will never equal 0. So that means x over x will always equal 1. You can see that these two canceled as well, so we're just left with a negative and an x. So this became a really easy limit. It's the limit as x goes to 0 from the right of -x. And that's just going to equal 0. Okay, for this example, we want to take these two fractions and we want to combine them into one fraction. Then when we do our limit, we can see what we're getting. Hopefully we get 0 over 0 or infinity over infinity, or maybe we'll just get a nice number. So let's see what happens when we do that. In order to combine these two fractions, we need a common denominator. So the first one is going to need an x minus 1 on the bottom. So we also have to put it on top. And the other one needs x plus 1. Again, if we put it on the bottom, we also have to put it on the top. Now that we have a common denominator, we can combine the tops. So we got to distribute the minus on both pieces. Now I want you to notice that the x squared is going to cancel with the minus x squared. So the top just becomes -2x. We have a -x minus x, so that's -2x. So again, this is just the pre-calculus part, but we are just rewriting this. So this fraction minus this fraction is just going to simplify to give us a -2x over x squared minus 1. And I'm going to erase that stuff at the bottom. Now that we've rewritten it, we can do the calculus part of it. If I try to do this limit, I'm going to get -infinity over infinity. So I can use L'Hopital's rule. This limit here is going to equal, according to L'Hopital's rule, this limit here. And this is just a plug-in limit. You're going to get a constant over infinity, and that's just going to equal 0. Okay, we're going to run through a bunch of examples real quick. This first one, if you were to do this limit, you would get infinity over infinity. So we can use L'Hopital's rule. The derivative of x is 1, and the derivative of e to the x is e to the x. Now this is just going to be a plug-in limit. If you plug in the infinity, you get 1 over infinity, and that's 0. Now this is the same example. The only difference is the e to the x is on the top and the x is on the bottom. So same thing, you would get infinity over infinity. So according to L'Hopital's rule, this limit is going to equal this limit here. Notice we did the derivative of the top and we did the derivative of the bottom separately. This is just a plug-in limit. Your final answer is just going to be e to the infinity, which is infinity. Now for this example, it's more of a word of caution. You got to be careful. If I plug in the 0, I'm going to get 0 over 1, which is just 0. Do not use L'Hopital's rule unless you have to. Remember, when you do your limit, you must get either 0 over 0 or infinity over infinity in order to use L'Hopital's rule. Here's another example where you should not use L'Hopital's rule. The limit as x goes to 0 from the left, for the top, it's approaching 1 from the left. For the bottom, it's approaching 0. So for this example, we're getting 1 over 0. We know that's either going to be infinity or negative infinity. So we have to figure out which one of those two is going to be our final answer. Remember, we're not using L'Hopital's rule here, so we just have to use a little bit of logic. You can break this up into two separate functions, e to the x, and then 1 over x. Now we already talked about how the limit as x goes to 0 from the left for e to the x is just going to equal 1, because it's approaching a height of 1 from the left. So when we do the limit of that part, we just get 1. And then times the limit as x goes to 0 from the left of 1 over x. So look at 1 over x. Look at what's happening. As x goes to 0 from the left, that function is approaching negative infinity. So this is actually just a plug-in limit, but you have to look at those graphs to figure out what's going on with each of those two things. So the answer to this limit is 1 times negative infinity, so we get negative infinity. This is a really tricky one. What's important about this limit is that it's not L'Hopital's rule. Okay, here's another basic example of L'Hopital's rule. If you plug in 0, you're going to get 3 minus 3 over 0. So that's 0 over 0. So you can use L'Hopital's rule. So this limit is going to equal this limit. Notice I did the derivative of the bottom separate, and I did the derivative of the top separately as well. Now when you plug in a 0, you're just going to get negative 9. Okay, here's another example where you plug in the negative infinity, and you're going to get infinity over infinity. So we can use L'Hopital's rule. The derivative of the top is 2x. The derivative of the bottom is negative e to the negative x. You can try it again, plug in the negative infinity. You're going to get negative infinity on the top, and you're going to get negative infinity on the bottom. So we can use L'Hopital's rule one more time. This limit is going to equal this limit according to L'Hopital's rule. The derivative of 2x is 2, and the derivative of the bottom is just going to be e to the negative x. Now this is just a plug-in limit. If you plug in negative infinity, you're going to get 2 over e to the infinity. So that's like 2 over infinity. Remember, a constant divided by infinity is just going to equal 0. Okay, last one. If you plug in a 1, you're going to get 0 over 0. So we can do L'Hopital's rule. This limit will equal this limit. Notice we're doing the derivative of the bottom separate, and we're doing the derivative of the top separately as well. Now when you plug in a 1, you're going to get 0 over 0. So we can use L'Hopital's rule one more time. The derivative of the bottom is pretty easy. You're just going to get a 2. In order to do the derivative of the top, you're going to need to rewrite it. Okay, when we do the derivative of the top, we're getting negative 1 over x squared. Now this is just a plug-in limit. If you plug in the 1, you're going to get negative 1 over 2. So final answer is negative 1/2. Now I do want to point out that when you do the derivative of a polynomial, it becomes smaller and smaller and smaller until it's just a constant. So the bottom will eventually disappear. When you do the derivative of ln of x, it just keeps getting more and more crazy. So that piece will never disappear. But the good news is when you do L'Hopital's rule, you're doing the derivative of the top independently of the bottom. So you're doing them separately. So even though the top is getting crazier and crazier, the bottom is becoming easier and easier. So eventually you're going to get a nice answer.